In this lecture, we're going to prove the two lemmas that we didn't prove in the last lecture, and then we're going to continue talking about properties of integrals. So, let's start with the easy lemma. If f, defined on this interval AB, is continuous, then for any epsilon greater than 0, there exists delta greater than 0, such that if P is a partition of AB with the mesh less than delta. So remember, each partition, we think of it as being an interval. So I take my interval AB, break it up into subintervals, and the mesh is just the maximum length of a subinterval. So here I'm just saying that the maximum length of a subinterval is less than delta, which is the same as saying that each of the subintervals has length less than delta. Okay, so for any positive epsilon, there exists a positive delta, such that if for any partition whose mesh is small, if I take the upper sum minus the lower sum, the absolute value is less than epsilon. So we know that, well, I don't need the absolute values here. The lower sum is less than or equal to the upper sum, so upper sum minus the lower sum is greater than or equal to 0. So I don't need the absolute values here. So I'm going to do the proof, and the proof is going to depend on the fact that any continuous function on a compact set is uniformly continuous. Okay? Since f is continuous and AB is compact, f is uniformly continuous. Okay. This means there exists delta greater than 0 such that if the distance from x to y is less than delta, here I'm obviously only talking about x and y in the domain of the function. Okay, so if x and y are in the domain and the distance is less than delta, then the distance here is less than epsilon divided by absolute value of b minus a. So this delta is the one that I want. Okay? So I should say fix epsilon greater than 0 here. Okay? So if the mesh of any, so take any partition whose mesh is less than delta, and now what this means is, so let's take a quick look. Right, so I have xi minus 1, xi. Right, so just think about the function. And just think about one of the intervals in this partition. Now the distance between x, so xi minus 1 is less than or equal to the mesh, which is less than delta, which means that for any x and y in this interval, the distance between x and y is less than delta. So if I take any 2 points out of the same interval in the partition, the distance between them is less than delta, okay, which means the distance between their outputs is less than this. So I could say mi equals f of ti, and lowercase mi equals f of si for some ti and si in this interval. So remember, capital Mi is the supremum of the function values on this interval. Because my function is continuous, that supremum is actually a maximum. So m sub I, the maximum function value on this interval, is f of ti for some ti in here. So let's just say, I don't know what it would be. So probably that would be ti. And then the minimum is lowercase mi. The lowercase mi is defined to be the infimum of the function values on this interval. But because the interval is compact and the function is continuous, the infimum is actually a minimum. And so maybe si would be here, where the minimum function value is. So capital M, lowercase m, they're going to be max and min values, which are f of something in the interval. Now, because they're in the interval and the length of the interval is less than delta, the distance from xi to ti is less than delta, and so the distance from f of ti to f of si is less than epsilon over absolute value b minus a. And now this is just capital Mi minus lowercase mi. Okay. I don't need the absolute values because I know the capital Mi is greater than or equal to the lowercase mi. So I have greater than or equal to here, and then less than epsilon over b minus a absolute value over here. So basically what we've established here is a very simple idea that we kind of had to do a little, put in the details, but the idea is if so I have this delta, which is a universal quantity over my entire interval. I know that if any 2 points in the interval have distance to each other less than delta, then the distance between the outputs is less than this epsilon over the length of the interval. If the mesh of my partition is less than delta, then anything that's happening inside a single interval, the function values are less than that apart. Okay? So what we're saying here is that kind of how much the function varies on any given interval is very small. It's less than this. Okay? So in any interval, because of this uniform continuity, the maximum and minimum are very close to each other. Okay? So now I'm going to do upper Riemann sum minus lower Riemann sum for this interval. This is equal to sum I goes from 1 to n, capital Mi times xi minus 1 minus sum I goes from 1 to n, lowercase mi xi minus 1. This is equal to sum I goes from 1 to n, capital Mi minus lowercase mi xi minus 1, and this is less than, okay, each xi minus 1 is a positive number, so if I replace capital Mi minus lowercase mi with something bigger, then the whole thing gets bigger. Okay. And now this is a telescoping sum. Right? It's xn minus xn minus 1 plus xn minus 1 plus minus xn minus 2 all the way down to plus x1 minus x0, which is xn minus x0, which is b minus a, and I don't need these absolute values. B is bigger than a. Okay, so I get epsilon b minus a times b minus a, which is just epsilon. That's the proof. So we proved the one lemma. So let's prove the next lemma. If FAB is continuous for any, then for any epsilon greater than 0, there exists delta greater than 0, such that if the mesh of some partition, just for any partition, I should say, for any partition P of AB with mesh less than delta, if I take the upper sum minus the upper integral in absolute value, I get less than epsilon, but I don't need absolute value because I know this upper Riemann sum is greater than or equal to the upper Riemann integral, because the Riemann integral is the infimum of things like this. So it's at least this small, possibly smaller. Okay. So I can put the absolute values here if I want to. So this proof is going to be in multiple stages. So the first thing that we want to do is kind of give the idea. So the idea is we're going to use uniform continuity just like we did before. So if my mesh is small, so I fix an epsilon and then I produce a delta using the uniform continuity the way I did in the proof of the previous lemma, and then I come up with a partition whose mesh is less than that delta, then I know that the supremum of function values on any interval minus the infimum of function values on any interval is less than epsilon over b minus a, or whatever else I want to choose. Okay, so we're going to start exactly the same way. And now I'm going to say choose epsilon delta as in the previous proof. Okay. And then what we're going to do is say let P be a partition whose mesh is less than delta, and then say AB f of x dx is approximately UFQ. Okay? So this is the infimum of these upper sums, so I can find a Q whose value is as close to this as I want, right? So, within epsilon of this. Okay? And now what I can do is say, well, I know this. Be more precise. There exists some partition Q satisfying these inequalities, because this this integral is defined to be the infimum of things like this, so I can find a thing like this which is satisfying this, and this is our proposition that we've been using since the beginning of the semester. Okay. So let R be Q union P. Okay. So fix P with mesh less than delta, I guess I should have said up here. Now let R be Q union P. I'll note that well, the upper Riemann integral is less than or equal to the upper Riemann sum for any partition, so I still have this. And as we said in last lecture, if I R is a refinement of Q, because it contains every point in Q, so if I refine a partition, the upper sum can only decrease, and we proved that in the last lecture. So I have epsilon plus a b f of x dx. So this upper sum with respect to the partition R still satisfies these two end inequalities, and now the R also contains all the points of P. Okay. So here's what we're going to do. So now I just have to prove that the distance from the upper sum with respect to R to the upper sum with respect to P is less than epsilon, and then I'll know that the distance from here to the upper sum with respect to P is less than 2 epsilon. Okay? So I'm going to start being a little less than complete. So let's say P is x0, x1, dot, 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 up to xn. And R is going to be x0, and then possibly some new points in between. So R contains all the points of P and possibly some new points. So here, so R could be x0 and then y1, y2, let's say I1, and then x1, and then x, and then yi1 plus 1, and then yi1 plus 2. And so the numbering gets a little tedious, but I've taken my x points, which were in P, and possibly added some new points in between, some new partition points. And so for my partition P, I'm going to have rectangles that look like this. Okay. And then for my partition R, I'm going to have rectangles that look like this that break at every one of these smaller integrals with the new endpoints. Okay. Now, the upper sum with respect to P minus the upper sum with respect to R, well, it's greater than or equal to 0 because R is a partition, or is a refinement of P. We know that if I take P and refine it, the upper sum can only decrease. So this is greater than or equal to this, and this difference is greater than or equal to 0. But now, I'm going to say, let's let R be, say, Z0, Z1, up to Z, let's say, Q. Do this. So, R, I've labeled the points and I've written out the upper Riemann sum for R. These are all just the Z's are the points of R, and the mi stars are going to be the suprema, right? The maxes on each interval for the refinement R. And now, so the point is these kind of the tops of these smaller rectangles, those are the mi stars, and then the points in this first upper Riemann sum, well, they're going to have just, over long stretches, they're going to have the same upper value. So I'm going to put an mi here. What I'm doing is I'm saying, I'll say xi minus 1 and xi, that interval in the p upper sum, I can split it up into the subintervals and they just have the same maximum value. So if xi minus 1 xi, some interval in the bigger partition p, and it has some maximum value here, and I can split that up into smaller pieces, and each one has the same maximum value. Okay? So over here, I have the same intervals, but they have the maxes that occur on the p interval, or the p partition, and then the over here I have the same intervals, but with the mi stars, which are the maxes for the refinement R. Okay? Now I'll go over here, sum I goes from 1 to Q, mi minus mi star. Okay? So the mi's are the maxes over the big intervals, and the mi stars are the maxes over the smaller intervals. But I know the bigger intervals, right, the length of the bigger intervals is less than or equal to the mesh of P, which was assumed to be less than delta. We chose a partition whose mesh was less than delta. So the quote-unquote big intervals still have length less than delta, which means that the max and the min on any big interval, the difference between those is less than epsilon over b minus a. Right? So we chose delta to be small enough that I still have here epsilon over b minus a. Okay? The maximum over this entire interval minus the maximum of the function over one of these subintervals here is less than this value, because the inputs between these are less than delta apart, and we chose delta to be small enough to guarantee this inequality here. And then I have zi minus 1, and just like in the previous proof, I get epsilon b minus a times b minus a. I get epsilon, and this gives the proof. Well, let me keep writing. So this tells me that nope, that's not what I wanted. The upper integral So each of these quantities is non-negative. I can go ahead and put absolute values and use triangle inequality, but I don't really need that because everything here was non-negative. And the first part was less than epsilon by this computation that we just did. The second part was less than epsilon because of our choice of Q and R. So because of this inequality here, the second part is less than epsilon, so I get less than 2 epsilon. Okay? And because epsilon was any positive number that I wanted, this is good enough for the proof. So that's the proof of the two lemmas from the previous lecture, and they both essentially just hinged upon the uniform continuity of this continuous function on a compact set.